Hi everyone. In this video, we'll talk about unit and integration testing. We will go through an example with a mystery function. So let's suppose that you get this code, and you just get this code and you just need to figure out what exactly it does and ensure that it has the proper outputs. Now, how would you go about this? My thinking is you want to get your hands dirty. So we start by looking at the function, and we realize it's not good code. There's no comments. The names are like F and Y and X. That's not really very helpful. We have to just figure out what the function does, and the best way to do that is by running experiments. So we'll just call F with various inputs and observe the outputs. So this is what I mean by getting your hands dirty. You actually have to open up the function and try different inputs to see what's going to happen. Okay, well, I'm just going to do f of 7 and 12 because it takes two ints. It looks like we have a long number as our output, and I guess it's of type int, but that's not really very helpful for us as human beings. So instead, maybe let's call f with smaller inputs and figure out what the answers are. So if I do f of 2, 3, I get 8, 2, 4, I get 16, 2, 5, I get 32, and so by varying the inputs just a little bit, just changing the y but not the x, we start to spot a pattern. So it looks like f of xy calculates x to the y. Let's see if that's actually true. All right, that looks good. I varied the x. I did f of 3, 2, and that gave me 9, f of 4, 2, and that gave me 16, and f of 5, 2, and that gave me 25. So that seems fine, but let's run a few more experiments. Now, f of xy, we suspect, is meant to compute x to the y, but it actually doesn't. And we run a few more experiments and figure out places that it fails. So this is where we have to think about things like boundary and equivalence testing and diabolical testing. So if I do f of negative 2, 3, and that gives me 8, that seems okay. Actually, it gives me negative 8, so that seems okay. F of negative 2, 2 gives me positive 4. That seems okay. But if I do f of 2, 0, it gives me 2, which is not 2 to the 0. And f of 2, negative 1 is 2, which is definitely not 2 to the negative 1. Well, if we expect this program to be the power function, we do notice that if we think about how x to the y is computed, then where x to the 0 is 1 and x to the y is x to the y minus 1 times x for all y greater than 0, then, and we want this to return an int, then it really doesn't make sense to be able to have negative exponents in the first place. So we really should add some code to this that allows us to raise an error, which we'll talk about more later. Now, the point of this example is to talk about unit testing, where we looked at a small chunk of code. Unit testing is the testing of individual hardware or software units or groups of related units. We focus only on the method, interleaved methods, how methods work together, and class level. This is generally done by the programmers, and it's what's called open box. So you can really just go line by line in your code and figure out whether each line of the code is working properly. Even though I showed just a way of running it where we just put in examples, the more formal way to do this is with JUnit, where you can run all these tests straight away by creating a test file. We've already talked about system testing, which is testing which is conducted on the whole complete integrated system, which evaluates a system compliance with whatever the requirements were. So the requirements, it's just the specifications of the program, and you generate tests from there. Now, in general, you would want such system testing to be done by some sort of external test group who can't actually really look at the code directly, but they're not corrupted by how they think the code should go. However, you can also, as a programmer, do your own system testing, and that's part of what we are doing in this class. All code has bugs in it. You write your program, you'll think about tests that you want to run, and you'll see whether the actual was equal to the expected, and if it wasn't, you can improve your program to take care of those cases. And eventually, you will pass all the tests that you have thought of. But this doesn't necessarily include every test that could possibly happen. There are really insidious bugs out there. So there's not really a concept of bug-free code. It's just code that's basically maintainable, and you hit deadlines and you have to deliver them. So at some point you do have to stop testing and hope that you have covered as many cases as is possible. Now, the more cases that you work on, the stronger guarantees you have for your code. Now, when you write your test cases, you'll put a unique identifier, which is just the name of the test method or the assert that you're doing. So we talked about system testing before, which is how you name your test. And in this case, with doing unit testing, you actually want to name the method or whatever the specific point is that you are asserting. Then you'll actually do the input into the program. So closed box has to do with how the user might interact with the program, whereas open box, you can have inputs to methods that are set up to test. So users may not have direct access to these methods, but as the programmer, you can set up tests that look at those methods only. As before, you'll have the expected output. You have the expected output of the whole program. You have the expected output of an individual method. And then you have the actual results. Now, with closed box, that's just what the user gets from the program. With open box, you can check various things. You can check the values. You can also check on the state via other methods. You can return the type as well, just figure out what the type is and see if that's correct, things like that. So there's not really a moral difference between system testing and unit testing. It's just that unit testing breaks it down and looks at individual pieces. Okay, with unit testing, the focus is on a single unit, whereas integration testing is on units working together, and normally just a couple of moving pieces. Now, in Java, that would be methods in a class or how classes interact with each other. Now, we've talked about the requirements, equivalence classes, and boundary values before, so these are the same things that we're now applying at unit level. To give a more Java-focused example, I'll set up a larger project for you. So you can pause the slides to make sure that you're following each of these steps, but essentially you need to have a folder which I'm naming project 0, and we're going to put bin, lib, src, and test inside those. Now, this is a kind of standard way to set things up, which is why we're doing it like this. Now, your main logic is going to go inside a file called taxreturn.java. Well, really, whatever you want to name it in general, but the example that I have here is tax return. And the second thing that you're going to do is get a jar file, and you'll put that inside lib. So the jar file you can get from the JUnit website, and in this case I'm using 1.6.2, although there are some newer versions out there, and that's the version I'm going to go with, 1.6.2. Now, inside the test folder that you created, you're going to create your file name with test attached to it. So I had taxreturn.java, and now I have taxreturn.test.java inside test. Once you've set this up, you have the environment. And the next step to do is to write a method inside taxreturn.java that actually calculates the tax on somebody. Let me explain the environment. Bin is to store all the class files that you're eventually going to compile. The test is for storing your Java test case files. src is for storing all the Java files that you create. And finally, lib is for third-party libraries that Java does not have built into it. So even though scanner is in Java, JUnit is not. That's why we need this jar file. So I'm assuming that you have the tax return code and you have something that would there's a function, a method that you've written called getTax. So this is to show you what the syntax of the test file would look like. At the very top, you have an import of JUnit's testing classes and methods. So import static org.junit.jupyter.api.A assertions.star and import org.junit.jupyter.api.T test. So JUnit files look the same as other Java programs, but there are some changes to the syntax. The difference basically between JUnit Java files and regular Java files is the difference in how the methods inside are made. So methods no longer have static associated with them, and they're just going to return void. There's what's called a decorator. It's at T test that tells Java that this is a test. And JUnit itself has some assert methods that check if the code works correctly. So in here I have assert equals. So JUnit is just a thing that is provided for you. It's an API for automating unit and integration testing. There are different versions of JUnit. In this video, we've used JUnit 5, which uses this new library called Jupyter. And the test case methods have that at test tag before each test method. So that's just what we're going to use for the rest of this class. As we saw, if there's a getTax method inside the tax return Java file, then I can create a method called test getTax, and I can call the getTax method and I can check to see if it's actually equal. So the one that I actually used is called assert equals, which is this one here. I have the expected value, the actual value, a delta, which tells me that it's close enough, and a string message, which is what's going to print out if you don't get the right answer. Other things that you could have in JUnit are to just see if a condition is true and print out a message if it's true. Same for false. You can do assert equals for int and char, which will be exactly equal. So depending on what the input and output types of your methods are, you may want to use these different kinds of assertions. Very quickly, there might be methods that throw exceptions to provide feedback about incorrect or invalid input. Going back to the exponent example, it might be the fact that if the client gives me a negative number, then I need to say that it's not acceptable. So JUnit as well has test methods that are explicitly for testing exceptions. Now, we haven't talked about try catch or throws exception or anything like that, but this will be useful later on. Let's analyze the JUnit assertions a little bit more. The first thing that you put in your assert equals is the expected value that you would get. And then you put the actual thing that you get, which you set by writing whatever the method call is. And then I have a string here that tells me what happens if the test fails, if it's not equal to the actual, if the expected is not equal to the actual value. Because this is a check for a double, I also have here an epsilon value that will tell me if two numbers are within some range close to each other. One thing I want you to notice is the program that you wrote, which was called tax return, can be imported into the current program. So the way I call tax return is taxreturn.getTax, which is a public static method that is inside tax return. So let's talk about compiling Java based on that system that I had you set up with the 4 folders. One way to compile is just to say javac and then your file name .java, that'll compile it, and then java.filename, right? So then that will run it. Because what happens when you do javac is it actually creates what's called a class file. and the class file is what gets run with Java. But if you have several folders, several files that you are trying to compile, you might end up with a lot of class files. Instead, what we are going to do is we are going to organize things by specifying the compilation folder, which is where the class files are going to end up living. So I have Java C as before, and then I'm telling you store in bin, and then set the class path to bin. In other words, the Java class file will end up in this folder that I've named bin. And then I have it find the Java file to actually compile it. And in this case, I'm in the top level folder. So this is something you would expect with ls, is that ls can find bin and it can find a source because they're in the folder that I've managed to create, and then it knows how to find that file underneath. Now, when we execute, we do almost exactly the same thing. We're going to do java cp-cp bin, which tells you where the class path is, and then run the Java class file. Now, we can do the same sort of compilation thing with our JUnit test Java programs. Here I have java c-d bin -cp, and then this is a little bit different. Inside quotes, I have bin ;lib /JUnit platform console standalone 1.6.2.jar, because that's where I saved the jar file. Test / whatever your file name is, test.java. This is the Windows version. Now, the other way to do it is if you had a Mac or Linux. The difference here is going to be that you have a colon instead of a semicolon. That's the main difference. And it depends on which version you have, you may or may not require the quotes around it. Now, finally, you need to run the test cases, which requires you to reference the JUnit jar file, the bin directory, and the test's class name. You'll do that with java-jar, and then in quotes, lib / your jar file name, -cp bin, -c java file name test. So the jar helps you find the JUnit and locate the class files, which are in bin, and then it will tell you what the actual class name is. So whatever your file was called, if you had java file name.java, you, by compiling, created java file name.class. And similarly, you had java file name test.java, and now you have java file name test.class. And that is living inside the bin file, the bin folder. Your JUnit output will give you feedback on your test results. So you should see a output that says, thanks for using JUnit, and then it has these square brackets and it tells you how many tests it started and how many tests it found successful and failed. So it has quite a little bit of information here. Now, mine actually says 1 test failed. So when that happens, you have to think either my code is wrong, or it is possible that your test is wrong. Your test could be checking the wrong thing. So these are 2 things that you have to go back and see what happened there. Those are the first lines of defense if you are finding a mistake like that with JUnit. Now, also in the future, I want to point out that a lot of classes are going to use an auto grader that has tests that it's determined to see how good an answer that you've given is. Now, these kinds of tests are usually hidden to students, so you write your own tests to get the best guarantees that you can. Once you have those working properly, there are hidden tests that a staff runs to see if it works correctly on the remainder of the inputs. You'll see it again in a 300 class and in a 400 level class. So as long as you're taking a computer science class that has programming in it, there is going to be a way that the code that you're writing and the projects that you're doing are going to be auto-graded. So that is all I have for you in terms of understanding JUnit and understanding what unit testing is for. Thanks for watching.